Let us start this lecture again a quotation from Albert Einstein. A person who has never made a mistake never tried anything new, and that is a very important one. And so, before starting our lecture today, let us recall what we learnt in the last lecture. And we discuss about basically the heat is one mode of energy interaction between system and surrounding, and which is basically due to the temperature gradient. And then we also find out like how it is different from the work and what are the similarities between the work and heat, and we learned that both the work and heat are basically path function. It does not depend on the what you call rather it is an inexact differential, and it will be what you call a boundary work. That means, a boundary interaction between the system and surrounding, it goes through the boundary. And then we moved into the how many thermodynamic variables one can vary independently for a system, and we state the state postulate. We say that number of thermodynamic properties that can be varied independently is equal to number of reversible work mode plus 1, and we have taken some examples and then to demonstrate that how it can be. And then we moved into the various ways of measuring temperature and also the importance of the temperature scale, which will be independent of thermometric fluid. And now, today we will be looking at basically the properties and related to the thermodynamics and how it is varied, because the properties only will tell us about the system's interaction with the surrounding and how it is doing and the state of the interactions can be judged by looking at the properties in a quantitative manner. So, to evaluate the degree of change, the system properties had to be known, right. And basically, because the change of state means change in properties, I mean thermodynamic properties. Let us look at a system which was it at state 1, it is can move through the path B, or it can move through the path C to the point 2, or it can move through the path A. The properties will be basically not dependent on the path taken by the system. It will be will be related to the point like where it is state 1 or state 2. Therefore, it is a point function. So, what are the kinds of thermodynamic properties we will be handling? In other words, how we can classify it? We can classify into two kinds. One is measurable properties like pressure, volume, temperature, all these things we can measure. But there will be some non-measurable properties like internal energy, enthalpy, entropy, Gibbs free energy, Helmholtz free energy and other things. So, these are non-measurable properties. So, we need to also learn how we can have those non-measurable properties by using the data of measurable property. That means, we need to create some ways and means of connecting both the measurable and non-measurable properties, that we will be doing little later on. But what here we will be doing these properties is basically for a pure substance, right. because substance can be various kinds, but we will be looking at pure substance. Question arises, what do you mean by pure substance, right? For example, if I say a brass and if I take a copper, right. Okay. So, can I call it as a pure substance? The brass is a pure substance or copper is a pure substance? Which one? Naturally copper. But is it that sense what we talk about here, right? So, what do you mean by a pure substance? For example, if I take nitrogen gas, right, and I take air, air having constituent of what? Oxygen, nitrogen mainly, right. It can be other gases, but we are neglecting other gases. So, can I call it as a pure substance? If I cannot, right? Na? Air I cannot say as a pure substance, am I right? Some of you people are agreeing to my statement that air cannot be a pure substance. We will see as we go along whether you are right or wrong, right. For example, I will take water and some oil, there is a lot of emulsions, emulsions kind of thing. I can take a biodiesel and diesel, we can mix, nowadays we are trying to mix that, or alcohol with your diesel, right, because of we can use that. And can we call those as a pure substance or not, that we will see. First of all, let us understand what do we mean by pure substance. A pure substance we can call, can define it as a, consist of a matter with a fixed chemical composition, right. It will be homogeneous in its composition, then we call it as a pure substance, right. Examples are water, nitrogen, helium, carbon dioxide, hydrogen, oxygen, any gas, because it will be homogeneous. If I take a cylinder of hydrogen gas, right. So, what will be its color? How we will know it is a hydrogen or a oxygen? I had suggested you to look at the symbol, right. I think you must not have looked at it, am I right? Please look at it. Suppose as an engineer, somebody will say, look, this is oxygen cylinder and this is hydrogen. You may say make a mistake. So, if you make a mistake, catastrophic will occur, am I right? So, you need to know the color code, and let us say it is hydrogen, if it is containing a contained in a cylinder, then it will be all uniform. So, therefore, I can call it as a pure substance. And as I asked earlier, can air be considered as a pure substance? Of course, it can be, provided the air is at the ambient temperature and pressure. If I take a air cylinder or air in this room, it will be uniform in chemical composition. You cannot separate the oxygen from nitrogen, unless you do some separation procedure, like, or some kind of a membrane you will have to use to separate it, or how I can separate oxygen from nitrogen? One can think of membrane, using. Is there any other way of doing it? How? You can think of liquefying it, right. If you liquefy it, then one can think of separating it out. So, therefore, it is at ambient temperature and pressure, it will be uniform in chemical composition. Therefore, we can call it as a what you call pure substance. Let us say if I say water and oil, right, it will be definitely what it will be. Can a mixture of water and oil be considered as pure substance? Similarly, if I take water and its vapor, right, can I call it as a pure substance? And if I take liquid air and its vapor, can I call it as a pure substance, right. So, which one? These are three examples I have given, right. Liquid air and its vapor, it cannot be really a pure substance, yes or no? Because some of the compositions between both the liquid air and its vapor need not to be same. So, therefore, it cannot be. And similarly, for water and this vapor, can we call it as a pure substance or not? We can definitely call, because it is the same water molecule will be there, whether it is a liquid state or a vapor state. So, therefore, we can call it as a pure substance, and water and oil we cannot really call it as a pure substance, because it is at different compositions. So, now whenever we are talking about, like we will be talking about a phase. So, what do you mean by phase? Phase is basically a distinct state in which matter remains homogeneous physically and chemically. Chemically, if it is homogeneous, what do we call? We call it as a pure substance, right. But here not only the chemically homogeneous, it should be physically as well. The common example, in summer season, you will be getting some ice water, right. If it is ice is there, then that is in solid phase and water will be in the liquid phase. This can be identified as a distinct molecular arrangement that is homogeneous throughout its boundary. As I told, the ice will be solid. So, it will be having a distinct boundary, and that boundary which will separate from its liquid, we call it as a what you call phase boundary. For example, if it is, I will take another example, this is a water and its vapor, and this is your phase boundary, where water can be converted into vapor, and there is a water label you can see, and that itself will be known as the phase boundary. So, the phase can be broadly divided into three categories. One is solid phase, liquid phase and vapor phase, right. And thermodynamic properties of a substance change abruptly at the phase boundary, right, yes or no. Although the certain properties like intensive properties, for example, pressure or temperature will be remaining constant. So, therefore, there will be change of certain properties of the substance across the boundaries. For example, if you look at water, right, and if you look at its specific volume of the water, will it be same as that of the its vapor? It will be very different, right. Will order of magnitude difference will be there. So, but whereas the pressure here, if I say it is ambient, you take a pan and then heat the water. So, if you look at ambient pressure is there and temperature will be what, maybe 100 degree Celsius, right. So, it will boil, it will vapors will come over, so that or vapors will be produced, so that it will be changing, right. That means, pressure and temperature remaining constant, however, the its specific volume will be changing. So, to make it more concrete, you can say that liquid water and vapor coexist at 100 degree Celsius 101.325 kilopascals, like properties like specific volume, internal energy, specific enthalpy, entropy are quite different across the its boundary, phase boundary. That means, there is a lot of difference of these properties. If you look at the numbers, both the liquid and vapor will be quite different, which we will see as we look at in this either in this lecture or in the next lecture we will be looking at it. So, let us look at phases of a pure substance. If you look at this is a solid kind of thing, and there is a which can be considered as a spring model, like these are the molecules which are sitting over here, and it is as if connected with a solid with a spring, connected with a spring, and these molecules in a solid are kept at their position kind of by large spring, like intermolecular forces. You can, this is a model, it is not that basically what will be existing between the molecules in a solid is the intermolecular forces, and which will be quite large, and there will be also the repulsive forces, right. Repulsive forces will be there only when these molecules will come very closer to each other. That means, the distance between the molecules will be tending towards 0, then you will get a repulsive. As a result, like they can move, and these molecules are basically will be vibrating, in these ways. It will be vibrating, and then these molecules are being repeated. This pattern, what we call it, is in lattice structures kind of things. It will be repeated, and they will be together kind of things, right. The intermolecular forces are quite high, right. If you consider that earlier days in our family system, there is a lot of intermolecular force, or man or the people things were there, they can take more resistance, right. If you apply a force, or a kind of thing stress, they can take, and today it is not, right, if you consider. And this can vibrate, as I told that this will be molecule will be vibrating over that, and when you will be giving some kind of a heat or the temperature will go up, what will happen? This vibration energy will be increasing, and when it is increases, then what happen? That velocity of the what you call molecules, or the which will be vibrating along with mean position, that will be increasing. As a result, it will go away from this, from their lattice, and then move with a certain patterns, and then you will get what you call the liquid state, and this liquid state, they will be togetherness, but they will be not in a fixed position like in your solid. So, therefore, it became a fluid or a liquid, and then if you go give more energy, then what will happen? That became separated out, and then the molecules will be far away, and they move in a random manner in the gas phases, and as a result, like they will be interacting, but they will be interacting very rarely, and by the interaction will take place through the what you call molecular collisions. If you look at in our country, that our earlier days, the people were having what you call lot of kind of forces, they were togetherness was there, and today after few years, like or what you call after maybe few years back we are liquid, now today we are gaseous state and moving randomly, although the each molecule having a higher energy level, right. So, this molecule will be having higher energy level, and therefore, we get a lot of stress and strain in our life. So, if you look at what I am trying to emphasize here, that solid is similar to our earlier culture of family, having a family or a village is having a lot of family bond was stronger. Today, it is broken, and therefore, we become gaseous state, and then we will be facing lot of problems. So, one has to look at that. So, now if you look at these things in the low temperature, like the solid phase will be there, atoms and molecule are held tightly in place, togetherness, and as it is temperature increases, we molecules will be separated from their place which were they are occupying in a very secured manner. That's and then the moved, of course, they will remain, molecules will remain together, but move relatively freely, not in the fixed position like a solid. But in the gas, when the temperature goes up, the atoms or molecule move essentially unconstrained, without any constraint they will be moving here and there. And of course, there is another state with the plasma states which are very, very high temperature. If you look at this is that the low temperature less than 100, here this became above 100 and other thing. Of course, for water it is 100, but for other metal it will be different temperature to liquid temperature, and then when you go to thousands and 10,000s kind of things, you will get a plasma state kind of things, and then it will be fully ionized plasma is a very high temperature. So, if you look at like this is the kind of phase change what it occurs, and we will be discussing more about that. And let us look at the all substances change their specific volume when subjected to change in pressure and temperature. And as I told that, like it will be changing. For example, if I take a solid rod which is in elastic nature, either I will give a force, right, or it is applied to a force, or it is applied to a temperature, there will be expansion, right. When it will remove that force or the temperature, then it will be contract. Now, that changes will be quite small, right. If I consider the what you call a gas where I will apply the pressure and where I will apply the temperature or the heat, then expansion will be very high. Therefore, the change in specific volume in case of solid and liquid is quite small as compared to the gas, and we call it as an incompressible fluid. And where it is change is very large, then we call it as a compressible fluid. Now, question arises how to characterize it quantitatively, right, because we will say look, it is a compressible substance or incompressible substance by just looking at the specific volume change with the change in the pressure or temperature kind of thing, but how we will quantify it? Unless we know quantification some number, we cannot really use it, right. So, for that we will have to define two terms. One is we are saying that the temperature is remaining constant, right. There are two variables which can make the same changes in the volume. So, therefore, we will have to keep one of them constant. We are saying that temperature is remaining constant and there will be change in volume with the application of the pressure I mean force here, and then will be change in volume per unit volume with the change in pressure when the temperature is remaining constant. We call it isothermal compressibility, and keep in mind that this is having a negative sign here. Why that negative sign? Because whenever you are applying a force, right, and trying to compress it, the volume will change, volume will decrease. Will it increase or decrease? It will definitely decrease. So, V 2 minus V 1 and V 2 is less than the V 1, therefore, negative signs comes over here. But we will just look at the another way of quantifying it, right. That is the coefficient of volume expansion, where pressure will be remaining constant and temperature is change. So, if you look at the beta is basically 1 over V into dou V by dou T when pressure is constant. So, if you look at this beta is having a positive quantities, and this is known as the coefficient of volume expansions, and this will be quite small if it is having incompressible substance. So, also the isothermal compressibility, if it is large we call it a compressible substance, right. And keep in mind that these properties or these quantities will be very useful for deriving these non-measurable properties by using the measurable properties. For example, volume, pressure, temperature, these are all measurable properties, right. We will be using these coefficients, either the isothermal compressibility or the coefficient of volume expansion. This will be using to connecting the non-measurable properties with the measurable property and vice versa. So, let us look at simple compressible substance which we will be dealing with in this course, and is one in which one relevant reversible work mode will be used, and we that is the simple compressible substance we call. And as we know the state postulate says that independent thermodynamic properties that can be varied is equal to number of independent work reversible work mode plus 1, right. So, in the simple compressible substance reversible work mode work is basically 1. So, therefore, the total number of properties that can be varied independently is 2 in this case, the simple compressible substance. So, most convenient properties will be what you call internal energy and specific volume, specific internal energy and specific volume. So, we can think of pressure is a function of internal energy and specific volume, temperature similarly function of specific internal energy and specific volume. So, also the entropy and other things, and which will be relating this to the what you call the other non measurable properties later on, and these relationships we call it as a fundamental relations, which will be looking at towards the end of this course. And by knowing these fundamental what you call properties or the fundamental relations, we can find out thermodynamic property of the system. And as I told that we will be discussing about these fundamental relations towards the end of this course. And but however, here we need to look at this thermodynamic properties in the mathematical relations, right. Either we can express in terms of mathematical relations, or we can use a what you call tables, data tables like your steam table, refrigeration data tables and other things. And we can also use some charts or diagrams, right, to describe the process and also use the properties. So, thermodynamic properties, as I told earlier, that can be determined experimentally at specific temperature and pressure by interpolation method and using these fundamental relations, which I have not discussed. We can relate these experimental properties with the non-experimental properties. Of course, another way of doing is that by using the statistical thermodynamic at a higher temperature, because all these properties what we will be using basically at the low temperature, because low temperature we can measure, but in the high temperature it is very difficult to measure. Let us say it is a something 10,000, 20,000 degrees Celsius you are talking about, you cannot really measure it. So, therefore, we need to use the statistical thermodynamics which we will not be discussing, but however, it can be done, right. So, now we will be looking at the phase change process in a pure substance. We will be considering the water as a substance to be discussed, the phase change processes, and that can be valid also for other pure substances. We will consider a case of water at 20 degrees Celsius in a piston and cylinder arrangement, what is shown here, and water will be at 20 degrees Celsius here, and the pressure which is applied is 0.1 megapascal. So, if I will go on adding to the heat, and if I take this as my system boundary, right. So, what will happen? What will happen to this water? What properties will be changing? So, if you look at this at 20 degrees Celsius, and what will happen to the temperature of the water? Definitely it will increase, you are giving heat, and what happens to the pressure? Will it increase? Will it decrease, or what will happen? It will be remaining what? Same, because you are applying the same 0.1 megapascal, it will not be changing. That means, here it will be constant pressure process one can think of, right. And then what happened to the specific volume? What will happen? volume will increase, right. But the increase will be not much, as we have seen that it will be water at this point will be incompressible, because very water we consider as an incompressible substance, right. And this state at 20 degree Celsius we call it subcooled state also. So, now what will happen if we will go on this temperature will be going up like 20 degree, 25 degree, like go on, and then there will be a temperature it will come, that is known as, like let us say it will reach the water temperature 99.6 degrees Celsius. What will happen at that point with the pressure equal to the point what you call 1 megapascal? What will happen? It will start boiling, right. Once you start boiling, what happens to its temperature? It will be remaining constant, temperature will not change. Then the water bubbles, which will be going up, and it will go up because it is right, and then collected, and then there will be the vaporization will start occurring, right. And once this vaporization occurs, what it will be? It will be a mixture of water and its vapor, right. And what happens to pressure? Pressure remain constant, temperature is also remaining constant, but the specific volume increases at a very high rate. Why? Because the specific volume of the vapor is 1 order magnitude higher than that of the water, right. So, here therefore, the volume will be increasing rapidly, kind of things. And keep in mind that all these things happening in a very quasi static process or quasi equilibrium process, right. If I look at, if I will take this heat out from this here, what will happen? Some of the vapor will condense back to the where? To the water. And similarly, heat I will take out, it will be known as the what you call, it will be temperature also will be reducing from the system. Whenever I am taking the heat from the system to surrounding, let us say it is at 50 degrees Celsius here, and then it will reduce, so that it can press back. So, if you look at this temperature increase here from let us say 20 degree Celsius to the higher temperature with the addition of heat to the system from its surrounding, we will call it as a sensible change in sensible enthalpy change, okay, because you can sense it. Here the temperature is remaining constant, although you are giving heat, you will go on giving heat, but still the temperature is remaining constant, because that heat what you give we call it latent heat. And how long this will go on? That means that even though you are giving heat to the system, but there is no change in temperature, although the specific volume will be go on increasing, right. How long it will go on this process? How long? Till the last drop of water is converted into its vapor, right. And in this case, if you go on giving heat, what will happen? The specific volume definitely will increase, right. And what happens to temperature? What happens to temperature? Temperature also will go on increasing, right. So, and this suppose in this case I will take it is last this thing some heat, then what will happen? This will be condensed back to the liquid, and it will get into this two phase situation, because this we call it as a wet mixture, because mixture of vapor and liquid in this case, and then it can come to the liquid. So, this process we can trace in a what you call TV diagram, this is the temperature, right, this is the volume. If you look at, we started here with 20 degree Celsius, right, and this we call it as a compressed liquid or subcooled liquid. Then the temperature is remaining constant, and this point we call it as a saturated liquid point, right. This point we call it as a saturated liquid point, and in this case there will be mixture of both the liquid and its vapor, and keep in mind that temperature is remaining constant, and this we call it as a saturated vapor line, vapor point. And as you go beyond this and add heat, there will be increase in the not only the specific volume, also the temperature, right. This we call it as a superheated vapor, right. And if I will conduct this experiment for different pressure, let us say if it is a lower pressure, what will happen? If it is a lower pressure, so it will be go on this kind of things. Point, and again it will go like that way. If it is higher pressure, what will happen? It will go on this ways. So, what is happening to this saturated vapor point? It is changing, and in this case the higher pressure, this is P, is greater than 1 atmosphere pressure, and here is P is less than 1 atmosphere pressure. I can say P here is 0.1 atm, and this is P is equal to 1 8 or 10 atm, okay, 10 atmosphere pressure, right. And if I will go on like that, what will happen? If I go on increasing pressure, what will happen? Let us say I will take a little higher pressure here, what will happen? What you are observing? So, that means this portion, the saturated mixtures are portion is decreasing, like these points are contracting or becoming lower, and this of course, it is occurring at higher specific volume, and these points are occurring at the lower specific volume. So, there will be a situation where the liquid will directly converted into what? Its vapor, right. So, let us look it further. So, I must emphasize this thing, that as I told earlier, that if the entire process between state 1 and 5 is reversed by cooling the water while maintaining the same pressure, water will go back to the state 1, right, tracing the same path. Then amount of heat release will be exactly same as the amount of heat added during the heating process, right. That is a very important point you should keep in mind. And the temperature at which the water starts boiling depends on the pressure. We have already seen that. Therefore, if the pressure is fixed, so is the boiling temperature, and the temperature, saturation temperature for 0.1 megapascal is basically 99.6 degree Celsius for water, and saturation pressure will be what you call 0.1 megapascal, for 99.6 degree Celsius water. It is just I am saying saturation temperature, saturation pressure, because it is corresponding to that. And for a pure substance, you can think of the saturation pressure, goes on increasing with the increase in temperature, right. So, what is its implication? Can I really learn something from this? Can you, or in other words, can you tell me, based on this simple principle, can we devise something which can be useful for us? See, you might be seen your mother uses the pressure cooker for cooking food. Am I right or wrong? Yes or no? You might be knowing, na? Aware or not? Why it is so? Pressure cooker, you must have seen, right? Yes or no? How many of you not seen pressure cooker? No, not a single. You have not seen pressure cooker in your home. I am really amazed by this. So, what will be the pressure in the pressure cooker? Any idea? Okay, let me ask you a question. Suppose you boil the dal in a pan which is subjected to atmospheric pressure, how much time it will take? It will be taking something, let us say, around 20 minutes. Okay? But if I use the same amount of dal and same amount of water in a pressure cooker, how much time it will take? Will it be higher or lower? It will be lower, let us say 5 minutes. That means what? Why it is taking? If you look at this curve, right, that means, let us say it is at a lower temperature, like kind of things, or lower pressure, something 100 kind of, right. Ambient temperature, if you look at, right, let us say this is, right, ambient temperature we have seen, ambient pressure we know that water will boil at 99.6 degree Celsius, right. So, at a higher pressure, what will happen to the saturation temperature? It will be higher, right. Yes or no? So, that if you are boiling at a higher temperature using a pressure cooker in which the pressure inside the pressure cooker will be higher than the atmospheric pressure, then you can cook it easily or quickly, right. Generally, 2 atmospheric pressure is being kept in a pressure cooker, domestic pressure cooker, right. But if you look at the nutrient values of those food will be much lower than the what? Lower than the what you can cook in the atmospheric pressure, but you want to have a fast. For example, let me ask you a question, it is very interesting. Suppose you cook in a pressure cooker and you cook in a solar cooker and you cook in a your general with a simple pan, same thing by the same person, which will be tastier? 3 cases I have told. So, which one will be tastier and why? You are not saying me anything, at least I was thinking you will tell me. No idea. Let me tell you that all these things will be cooked at a low, like in the solar cooker, temperature at which the food will be cooked is much lower. In the simple pan with using LPG stove or any other stove, right, will be at higher temperature, and the pressure cooker will be at highest temperature among all these 3. Okay. So, where the food will be tastier? Solar cooker, right. You got the point. Why it is? Because the temperature gradient is very low. So, also in our life, that when we are subjected to the less gradient, we perform better. Okay. So, that is the important point we should keep in mind, and that is the application of thermodynamics. Similarly, the saturation, you can think of several of examples, one can think of cooling and getting ice, right, and from the water. By lowering the pressure, I can get ice just by lowering the pressure. If I will go to the vacuum, the water become converted into ice and several other things. So, as I was telling that these are the points is the saturated liquid point, and similarly these points are the saturated vapor points at different pressures. As if you look at these zones goes on decreasing, and there is a point where the liquid, if you look at these are the basically liquid, right, it will be converted into gas, and that point, that is corresponding to the 22.06 megapascals and the temperature of 373.95 degrees Celsius, right, where the liquid will instantly converted into vapor. That means, the specific volume of the liquid and its vapor is same. Are you getting my point? That means, at this point, the critical point here, the V g is equal to V f. V f means is a liquid, specific volume of the liquid is same, and this critical point is very important, right, because that will tell me whether it is a liquid or the vapor, and that is the kind of things. And if you look at this is liquid, and above this point we call it as a vapor, and above this point all this vapor will be, we call it superheated what you call vapor kind of things. And if you do that, then you will not having this wet mixture. This is known as wet mixture. Wet mixture means is the mixture of liquid and its vapor, and that will be corroded, and we will be discussing that maybe whenever we are talking about power plant, steam power plant, and boiler, like we will be encountering these mixtures, it will corrode it and other problems. Nowadays people are thinking of using, or rather they are using, not thinking, they are using supercritical boilers, because they will be operating at a very, very high pressure. So, that liquid it will instantly get into the vapor, and you will not, you will avoid the mixture of the wet or wet mixture of the vapor and liquid. So, if I join this line points, right, if I join these points, right, this is known as, this line known as what? Saturated liquid line. This line is known as saturated liquid line. And similarly, if I join these points over here in these points, this is known as saturated vapor line. And keep in mind, this slope is steep and this is little flat, and that indicates that in between these two lines the mixture, that means wet mixture will be there, mixture of vapor and water will be there. And question arises, what would be the like percentage of water, what will be percentage of vapor? In this case, the percentage of vapor will be 0. Here the percentage of vapor will be in this point will be 100%, right. So, we will be defining a quantities for that, and also look at how to find out these properties, because we will be interested in evaluating the properties in these mixtures also, like internal energy, enthalpy, entropy, all those properties we need to evaluate. So, what will be available here, the properties will be available here and properties will be available there, but we need to know this and then find it out. That is the challenge, we will have to look at how we will do that. So, just to say that what are the critical point pressure and temperature data, let us look at some of the data here. Like water, I have already told you the critical temperature is 647.39 at critical pressure of 22.07 megapascals, and this is the critical volume. And various other substances I have put it, I have placed it in this table, that is carbon dioxide, oxygen, hydrogen and helium. Interestingly, if you will find the critical temperature for helium is very, very low, 5.3 Kelvin, and so also the pressure is something 0.23 megapascals. Of course, the if you look at the others are in between, but most of the metals have higher critical temperature than water, because like it is having what to call this thing. So, they are having higher metal critical temperatures at which it will be vaporizing. So, just to have a feel for this, what I am saying that this will be what you call, just to summarize this, and we will say that this is your saturated liquid line and this is your saturated vapor line, and this is your constant pressure line, P is constant, and this is your constant another constant pressure line, that P 2 is greater than P 1, and this, as I told, that this will be basically compressed liquid region we call, and people also call it as a subcooled liquid region, subcooled or compressed liquid region we call, and this is your superheated vapor region, right. And we do always try to use in your power plant superheated vapors, kind of things. We need to avoid this mixture, saturated liquid and vapor mixtures. So, this is in a TV diagram where the properties, like where this can be processes can be described. And let us look at the saturated liquid and vapor mixtures kind of things, like because as I told, we will be interested to look at the how to handle this here saturated liquid and vapor mixtures. So, we will define a quantity, right, which is x, I call, that is nothing but mass of the vapor divided by mass of total mass. Mass means total mass means mass of the liquid, right. This is the mass of liquid and this is the mass of gas or the vapor, right. So, this we call it as a quality. What it indicates? It indicates that how much of mass of vapor is there with respect to the total mass of the mixture, and we will be using this symbol F for the liquid, okay, because historically this is being used, and it is the meaning is basically liquid, because in German this word has come from Prages. So, kind of things, and this x quality, if you look at this, is we call it the steam quality, steam quality. So, which will be, as I told, that x will be becoming 0 here, right, and this will be 1 here. X quality will be 0 here and 1 here, in between it will be between 0 and 1. It can be 0.1, it can be 0.2, it can be 0.5. 0.1 means the if there is a 1 kg of mass, this will be 1.1 kg will be the gas or the vapor in that. So, let us look at the V total volume becoming basically mass of the fluid into specific volume plus mass of the gas into specific volume of the gas, and we know this mass, total mass will be mass of liquid plus mass of gas, and if I divide this by the mass, what will happen? And this is, if you look at what is this by definition, this is nothing but your mg by m. M is the mass of the mixtures, right, and mg is the vapor. What is this? This is nothing but your x, right, quality, steam quality or the, right. So, then I can write down this is nothing but your, this is become 1, and as I told, this is nothing but your x. So, this is mf by m plus x, right. So, I can write down that mf by m is nothing but 1 minus x, and if I will put this thing here, this term over here, and this x, this is nothing but your x, this is nothing but your x. So, I can find out the specific volume is nothing but 1 minus x V f plus x V g, right. And we can also write down V f plus x V f g, V f g is nothing but V g minus V f, right. So, therefore, the x one can define V minus V f divided by V g minus V f. So, if you look at, as I told earlier, that x is basically 0 here and x is 1. So, therefore, at any point I can find out that x is equal to V minus V m V f, right. So, this is the basically V here and this is your V f at this point and this is your V g divided by V f g, the difference will give me the x. So, as I know this quality, right, x, then I can, knowing this thing, I can find out all other properties like internal energy, enthalpy, entropy, because if I know this V u g at this point, at this point u z and u f at this point, I can find out in between. Similarly, enthalpy, entropy and other things. So, we will be using this quality in our calculation later on, and by knowing this quality we can find out properties of the weight mixtures, right. So, I will stop over here and we will discuss further in the next lecture.